Welcome. Today I'm going to present you with a combined zero-shot and fine-tuned model for text classification. This work was motivated by the recent progress of the pre-trained natural language models such as BERT and GPT and the improved accuracy after fine-tuning. However, this model has not been applied in a lot of text classification problems in the real world because the data that we see in day-to-day basis have a lot of distribution bias that diminish the accuracy. In this study, we developed a deep learning model that combines the weights of a zero-shot model, which is generalizable, and a fine-tuned model that's more accurate. Both of these models are based on sentence BERT, which is a pre-trained natural language model that's tailored for sentence-based tasks. The combined approach has recently shown some interesting simultaneous improvement in both generalizability and accuracy in image classification tasks. This was presented in CVPR 2022, and we want to see whether that works in language models as well. The inputs of the model was the text to be classified and the class candidates. Then the output was a ranking of the cosine similarities between the text and each class candidates. We tested accuracy based on whether the top three class candidates in the ranking aligns with the real classification. The resulting model both increase the generalizability and accuracy. The generalizability, which is defined by the average accuracy of off-distribution datasets, increased from 59.8% to 62.4%, and it didn't come with a cost for in-distribution accuracy. It only decreased from 67% to 66%, not too much. The data sets we used include 4 different ones. The first one is Yahoo Answers, which is the in-distribution data sets that were used for training, validation, and testing. So we use this data set for fine-tuning. Then we used the 3 other data sets for validation and testing only. The features of these models really comes from the sentence BERT model that you can see from the publication. They are very well trained for sentence-based tasks, and they are tailored for cosine similarity calculation mathematically. And these are actually abstract embeddings. That's a feature vector of size 512. We don't know what's the real meaning of it, but we can calculate cosine similarities and compare between different sentences of different construct, but similar meanings. These features were then used for subsequent model development that we used. We developed the 3 models. The baseline model is a zero-shot model, which is basically a sentence BERT. Then we fine-tuned these models by fine-tuning the last 3 layers of sentence BERT with a decayed learning rate. Then we combined these models with an approach we called WISE-FT. WISE stands for ensembling the weights of zero-shot and fine-tuned models. It sounds complicated, but the idea is simple. It's basically taking the weighted average of the weights of zero-shot and fine-tuned model. We use the alpha to represent the fraction of the weights of the fine-tuned model. Therefore, 1 minus alpha is the fraction of weights in the zero-shot model. We calculated the resulting model using alpha from 0.0 to 1 with an interval of 0.1 and calculate the accuracy with a validation data set. If we look at the validation accuracy, the result is very interesting. X-axis is the in-distribution accuracy. Y-axis is the generalizability, which is calculated based on the average accuracy of the 3 off-distribution data sets. We chose 0.2, which means 20% fine-tuned model and 80% zero-shot model as the final model, because what you can see is that compared to the zero-shot model, it drastically increased the validation accuracy, and it actually increased the generalizability as well. Compared to the fine-tuned model, it drastically increased the generalizability on the y-axis, but it doesn't diminish the accuracy that much. That's why we chose it. When we look at the testing arrow with a standalone, the set-aside testing set, the conclusion was very similar. We both increased the generalizability and the accuracy based on the testing arrow in the in-distribution data set and the off-distribution data set. The result shows that really by adding a very small fraction of fine-tuned model, 20%, into the weights of the zero-shot model, we can simultaneously improve the in-distribution and off-distribution accuracy of text classification models. This will improve the generalizability and help us use these models in the day-to-day world. If we have another 6 months, we'll try to use other pre-trained models such as GPT-2 or GPT-3, which work great for chatbot. We want to see whether that works for text classification and whether that works better than sentence BERT. And that's about the work. Thanks for listening.